Just having a little bit closer look at 18-fluorodeoxyglucose. Okay, so it's a molecule, and we have a replacement of one of our groups, this fluorine atom here. You can see the fluorine atom that's been added in place of a OH group. This fluorine atom is a positron emitter, so it's positive. It emits positrons, which then go to the nearby electrons and annihilate, giving us our two gamma rays, which are then detected by our PET machine camera. Just have a look here, a closer look, and you can see it's just one of the groups that has been replaced, one of the OH or hydroxide groups. It's been replaced with fluorine 18, which is an isotope that produces positrons. And we also know, if we move that out of the way, glucose is good for looking at various organs because it's metabolized well. That's most cells take it into the body. It's soluble, moves around in the bloodstream very easily, and it's readily taken up by tissues such as the brain and heart, but also tumours, because they're using more fuel or more of the raw materials needed to grow. Glucose, one of those. It's actually the vital part for respiration. So the tumours are growing so fast that they're using, along with these other things, a lot of glucose. So as the glucose is used up, producing carbon dioxide and water, the fluorine is left behind in the tissues, and that's the thing that's being scanned for, because it's producing our gamma rays. It's also good because it has a relatively short half-life, and which means I think it's about 110 minutes or so. So it can be sent to hospitals within reach of the production facility in Australia. Ensto has cyclotron. Remember, fluorine is produced in a cyclotron. It has added protons. That enables hospitals to use the PET scanning facilities on a daily basis. Here you can see a PET image. The PET image is the one here. The other image, it's a little bit pixelated, but it's from a CAT scan, if you remember, computer axial tomography, computer mapping using X-rays. That's the one where the X-ray machine goes around the patient and takes scans through the object. They're both done in slices, so various slices can be looked at. The PET scan, however, one that we're interested in, shows different areas of the brain lighting up, and that's because they're using more of the glucose that's tagged with fluorine 18, FDG it's called, 18 FDG, fluorodeoxyglucose. The CAT scans, however, two black and white images, only really show structure. They do manage to get through the bone, which is very white, but you've got the brain material it's more difficult to see, but the quality is not as high as in an MRI. The PET scan, however, shows areas lighting up when the patient is asked questions or asked to do something. Extra blood flow goes to that part of the brain carrying glucose, depositing the glucose with the fluoro-18, and you get that annihilation of positron and electron in those areas, producing your two gamma rays at 180 degrees to each other. So that 180 degree effect there is the computer decides where the hotspots are, and if the blood flow changes or other areas of the brain uptake more of that fluorodeoxyglucose 18, they'll show up as hotspots. And this is good because it shows the function of the brain, whereas the X-ray or CAT scan image shows mainly just structure, different qualities of different parts. Bone absorbs more X-rays obviously, but the structure is the only thing being shown. Image, you can see a CAT scan, or CT scan it used to be called, but CAT scan we're calling it, computer axial tomography. It goes around the patient. The patient acts like an axis, it goes around, axle or wheel. We have a tumour here, but as you can see, it's not made of bone. It's not going to show up as clearly in a CAT scan. Remember, X-rays are absorbed predominantly by bone, somewhat by soft tissue and other changed or harder tissues, more dense tissues. But look over at the PET scan, it's producing a hot spot because it's taking up a lot more of the fluorodeoxyglucose. And then it's producing those two gamma rays at 180 degrees from our electron positron annihilation. So in this case, the PET scan is actually better for detecting brain tumours than the CT scan. A trained diagnostician or doctor, professor, would probably be able to use either, but clearly if it's a very small tumour, it might show up better as a hotspot, producing more of these gamma rays in a PET scan. Just one more thing on this particular one. An X-ray uses external sources of radiation, so it passes X-rays through, and those that don't make it through or absorbed leave an image. So more absorbed here. Ones that do get through are less bright, so they'll leave an image of an X-ray. Then it passes around the patient and does the same from all angles. External source. The PET scan uses an internal source of radiation. And we said that is our tagged glucose molecule. So it's producing it straight from the tumour out, and is often much more reliable in detecting tumours or bone tumours or metastases, we say tumour growing through tissues, than an X-ray which just takes the structure. The whole body PET scan, a person had multiple metastases or tumorous growths through the body. The brain and the bladder may have some residual substance that's been excreted from the body. The brain itself is using more glucose than other tissues in the body. It relies on, after all, the brain uses about a third of your food intake to run. But these other hotspots you can see maybe in the spine, glands, nodes, and the liver. We have quite a few tumours growing, and they're able to be seen because the tumour is using more glucose, as the brain does, than the rest of the body. If there are tumours in the brain, that will require not a whole body scan, but just a scan of the cranium or the head. Picture also shows us the value of seeing the function of these organs. They're taking up more glucose than is normal. The tumours are taking up more, so they stand out. And that's the function of them. They're taking in more of this tagged glucose. An X-ray would just pass through, and anything that has the right density, such as bone, would block the X-rays from developing the film.